Okay, so let's get started. So this is the very first part of the course. Um, this is section 1.1, and section 1.1 is covering the circuit theory in general. So this course is all or this course is about circuit theory, and for circuit theory is actually, you may ask yourself, what is the circuit theory? So circuit theory is actually a mathematical model that approximates the behavior of electric system. Or like an electric circuit is a mathematical model that approximates the behavior of an actual electric system. So physically, you can't find any, I mean, electric circuit is not something that you define. It's kind of like a mathematical model, because in general, what you have is the following. You kind of like you have physical system, and then you model it mathematically. This model will help you to study and analyze and design your system. And if your system is electrical system, then the mathematical model is called electric circuit. The topic that we're going to cover in this course is a special case of a very general theory. It's called electromagnetic field theory. And electromagnetic field theory is thoroughly discussed in Physics 305, EE 340, or Physics 306. And throughout this course, and almost in all of the analysis that you're going to see in all of the 200 level courses, you are assuming that you have electric circuit, you have circuit theory, you have this special case. You don't have the electromagnetic field theory. And for this assumption to hold, you have to have three important criteria. The first one is the circuit parameter must be smaller than the wavelength of operation. We'll talk about the wavelength. The wavelength is from Physics 102, is related to the frequency. It's actually the distance that the waves covers in space before it completes one oscillation or one cycle. So if in electrical engineering or in electromagnetic field theory, we always measure things not by height, not by length, but by wavelength. If something is very long, is very large at very low frequencies, at very high frequencies, it doesn't mean that it's very long, it's very large at very low frequencies. So that's one thing. So we want to make sure that our circuits or our system or the parameters that we're studying are much simpler than the wavelength of operation. This is true if we have a DC source or a DC circuit. What do we mean by DC? DC circuit is a circuit. DC stands for direct current. So current and voltage are constant with respect to time. So if we have a DC circuit, it means that the frequency, first of all, it will not repeat because it's going to be constant all over time. So the period will be infinity. So the frequency will be 0, and the wavelength will be infinity. Again, the wavelength is proportional to the frequency, 1 over the frequency. So if we have a DC circuit, then if we have a DC source, DC voltage source, or DC current source, it means they're constant with respect to time. Then we can apply a circuit theory because every parameter that we have is smaller than the wavelength. That's one condition. So this condition is satisfied. The second one is the net component or the net charge in every component of the system must be 0. And the most important thing is, or like that, the last condition is that no magnetic coupling between circuit elements. So what happens usually if you have a wire that carries current and another wire that carries that's just like or another wire that's carrying another current, then in the between them, or let's say you have a wire that carries current that's varying with respect to time, and then you have a wire next to it, not very far away from that, you will see that from Faraday's law, that there will be a current, there will be a magnetic field generated in the wire that's carrying the current, and that magnetic field will generate a current in the nearby wire. So there will be coupling between these two elements. And in order to apply circuit theory, we assume that there is no magnetic coupling between the circuit elements, and this achieved by placing the elements further apart. So don't worry about this. This is just like a general idea. So you might, I just said, like in reality, there is no electric circuit. So you have an electric system, and that system is modeled using electric circuit. So let's consider this example. So you have a system. When you touch this one or this metal, there will be a sensor, and that sensor will turn the LED on. So it's kind of like sensing whether you touch this metal plate or not. So if you want to get the big picture, you would say that I have an LED, a light bulb, I have a touching pad here, and I have a system here. So that's a sensor here. So that's the entire system. So if you want to actually model this system and design this system, we need to actually find mathematical models for that. And that's what we do with the circuit diagram. So the circuit diagram will consist of, for example, capacitor, diodes, resistors, amplifier, comparators, etc. And those elements or those circuit diagrams, circuit components, are kind of like mathematical models of the actual physical system. So now we design our system. We know that it's going to give us, if you touch this pad, the LED will turn on. And we want to turn it into a final product. So in order to do that, you're not going to give, if you are selling this product to a customer, you're not going to give him this circuit diagram. You're going to give him something physical, something that he can hold, something he can test. And in order to do that, we usually use a technique called printed circuit board. So you use kind of like fiberglass as an insulator. And on top of that, and maybe in the bottom, and sometimes in the middle, you kind of like created some sort of cables, and you place the components here. So you have discrete components. For example, you have a capacitor, which is this one. You have a IC, which is that one, and that's the component that you are selling. So designing in general, so what happens is the following: you have a bigger system, then you visualize it and understand it, design it using by drawing the circuit diagram and applying circuit theory. Then you build it. So in this course, we are concerned in this part. We will not worry about this part or that part. Okay, any question? Okay, so you may ask yourself how to succeed in this course. And I did kind of like, from my experience as a student, I kind of like found this, these steps are very, very useful and very important. So the very first thing is you need to master the fundamental concept in this course. So just look for the fundamental concept and make sure that you master these concepts. So you cannot just like solve problems and get away with that. Because if we change some of the problems to be something that's different from the one that you studied, and you don't know anything about the concept, or you did not master the concept, then you will be lost. So you need to focus on the fundamental concepts of the course. Those are voltage, current, charges, series, parallel combination, Ohm's law, KVL, and KCL. Then you need to solve intelligently as many problems as possible. And this is very important. Solving too many problems without actually understanding those problems just for the sake of solving is a waste of time. So you'd rather solve 5 problems, practice with 5 problems, and you understand everything about these problems, than solving 20 problems, just like looking into the solution and try to copy the solution. So just solve intelligently as many problems as possible. And a very important thing is I noticed is if you participate during lectures, then most of the vague concepts that were not clear, can be clarified. And this will help you in reducing the time you need to study the course. Although I'm going to post the slides on a Blackboard, it's very important that you write your own notes during the lecture. It's very important. I will also upload the lecture videos on the Microsoft stream, but you're going to be wasting your time if you attend this lecture and then you watch it. So it's okay to watch the lecture if something wasn't clear, 1 or 2 points is not clear, but don't make it a habit. Pay attention, try to get as much as possible from attending the lecture during the lecture time, and avoid watching the videos. Also, please refer to your textbook, and it's very important that you think and think and think before solving any problem. There are some strategies associated with the problem solving, and it's actually in the book. Yes.
الدكتور بس عندي سؤالي لو سمحت. بالنسبة للي هو solve intelligently as many problems as possible. Is there any suggested exercises like in the syllabus? I didn't see some problems that are focused on, so I don't know exactly what are the problems that I should solve.
Okay, very good question. So we're going to post on a Blackboard some of the sample problems, sample exercises. Those are one thing. The other thing is actually the examples in the book. So the book contains example and practice problems. So with the solution, some of them with the final solution. So you can actually work. You can use them to
okay, and another question, please. Is the theory important? Like I know that this course focus on the math, the calculations, and so on. But is the theory itself that should I memorize the definitions of a few?
No, you don't need to memorize. You need to understand.
Okay, thank you.
The difference between So what matters at the end is not how you solve problems or how many mathematical calculations that you can accomplish within a few minutes. What matters the most is you will see that in most cases, and most of the questions is actually, if you got the concept, then the problem will become easy. If you don't get the concept, then the problem will not be easy. So it's always
All
good.
right. Good,
Yes.
thank you.
Yes, Abdulaziz. Abdulaziz,
Hey,
yes.
doctor, do I need to revise what I studied in Physics 102 with
No.
regards to electric?
No, everything we're going to cover. If we need anything from Physics 102, we're going to cover. Yes, sir.
Will there be a recitation class or like a class to solve problems, or will we solve problems at the end of each class?
We're going to solve problems during the class.
Mm-hmm.
There will be practice problems, and from time to time I might have like a session for problem solving.
Okay, thank you.
Good. Okay, so let's move to the second topic, which is SI units. So for SI units, it's very important that we have a standard or a unified unit. If I say something is tall, we always have like common ground for all of our measurements. So which are tall in terms of, we say like something is 1.5 meter tall. You understand that it's what's 1 meter. What's the unit of 1 meter? I understand what's the unit of 1 meter. So we have a common ground for our measurement. Imagine that I created some sort of a unit for time. I say like time is measured by E/1. This is a unit I created. And they said the time it took me to go from my office to my home is 20 E/1. And it's really hard for you to imagine what's that unit, E/1, because it's a unit that we haven't agreed on. But if I said that it took me 20 minutes to go from my office to my home, then you will understand that that's the time. You have kind of like a reference for that. So it's very important that we have a common ground for all measurements. And it's very important that it's very important that kind of like we don't want to abuse these kind of units. So what happens is the following: there will be like there are seven fundamental units, 7 fundamental SI units for length, mass, time, electric current, thermodynamics, temperature, amount of substance, and luminous intensity. And those are the fundamental units, and all other units were derived from these 7 fundamental SI units. So for example, in this course, we're going to use, I believe, mass and time extensively, and electric current. So we're going to use electric current as it is, the unit as it is, time as the unit as it is, but a very important quantity that we have is actually the frequency, which we're going to utilize at the end of the course. And this unit is 1/2. So it's derived from a fundamental limit, which is second. The other unit that we're going to utilize is actually the energy. So the energy is derived from another unit, which is force. Force is derived from three fundamental SI units: from the mass, which is kilogram, from the length, and from the time. And you see the pattern repeats itself. So we have 7 fundamental units, and all other units will be derived from those units. Another common thing that we're going to see in this course is the use of prefixes. Oftentimes you will see a resistor in kilo ohms. So when you say kilo, means 10 to the power 3, or current that's in terms of milliamperes. And when you say milli, it's 10 to the power -3. So make sure that you know these. Probably the most important thing is milli, micro, nano, pico, kilo, and that we're going to see something with mega. Okay, this is something that we are all familiar with. Probably have studied in chemistry 101, physics 101. So it's just like restating the obvious. So the very first thing that we're going to cover that's not part of the thing that we've covered before is actually the definition for the charges, current, and voltage. So let's start with electric charges. Electric charges are very important and very fundamental, and they are the building blocks for all of the analysis in this course. So all of this course is about electric charges. There are two things associated with electric charge, or two kind of like behaviors that we want to study. We want to study the force between two charges, positive and negative, or positive or positive. And we want to study this what happens when we have stationary charges that are stationary, that they are not moving. The other behavior that we want to study is the behavior of moving charges. We have a charge that's moving between point A in space and point B. So for the force, we're talking about the force between charges will create an electric field, and this electric field is related to something very important in this course, which is voltage. Charges that are moving will create a current, and this current will generate magnetic field. So in this lecture, on this course, we're going to focus on the voltage and the current. Electric and magnetic field are left for EE. I think you all found the new curriculum, so they are left for physics 305. So again, this is what happens when we study the force between charges. We'll have the voltage. We are talking about the voltage. When we study the motion of charges, we are talking about the current. So charges are very important. So let's talk more about charges. All matters must contain positively charged protons, negatively charged electrons, and neutrons. So you can see here that we have two types of charges, positive and negative charges. So that's the kind of like the a simple model for an atom. We have a positively charged nucleus and we have an electron that's spinning around that nucleus. So electric charges do not exist in a continuous, they exist in discrete quantities. And these discrete quantities are integer multiple of this number, which is 1.6022 times 10 to the power negative 19. The unit is coulombs. And a very important thing that we're going to utilize when we derive something called Kirchhoff's current law is that charges are conserved, meaning that the net charge in a closed region must be can neither be created or nor destroyed, meaning that the net charge in a closed region must be 0. And this is something that we are all familiar with. When we have like charges, they will repel one another. When we have dislike charges, they will attract one another. So if you have a positive charge and negative charge, they will attract one another. If we have a negative charge and a negative charge, that they will repel each other. If we have a positive charge and a positive charge, they will repel each other. So the force between like charges, it's a repulsion force. The force between unlike charges or dislike charges is actually an attractive force. So any question? Okay. So now we know about charges. They are the fundamental building blocks. So let's study what happens when charges are moving. And this is the definition of the current. Yes.
دكتور العدد الموجود هو عدد الإلكترونات بالذرة بأي ذرة؟
No, this is the charge of the electron.
Yeah, I mean, is that means the amount of electrons for per nucleus?
No, this is the charge of the electron.
Yeah, thanks.
Okay. So what happens when we have charges that are moving? So if we study the rate of movement of electric charges or the rate of electric charge flow, this is the definition of the current. So the current is defined as the rate. When we say the rate, we mean that derivative with respect to time of the electric charge flow. So if we have more charges that flow in a short period of time, we should have more current. If we have few charges that flow in a long period of time, we'll have small current. So the current is actually the rate of electric charge flow. So current is the symbol for current is I, and the unit is amperes. After the French physicist Ampere, the unit of charge is coulombs. I think it's after the. I think he's a French. After the physicist Coulomb. And the unit of time is we are all familiar with this seconds. So maybe the easiest way to think about the current is to think about water flowing. So if you have water that flows from point A to point B, then usually water flows from the high region to the low region in a natural way. So if you have a natural water flowing, then the water will flow from the high region to the low region. If you want to do the opposite, you need to apply an external force. So it's very important to use this analogy. So when you say high region and low region, in the electrical engineering language, we're talking about high voltage, and we're talking about low voltage. So let's take an example here. Yes. So we have the following situation. We have the following figure, and in this figure we have a current. First of all, we have no charge at t for t less than 0. At t equals to 0, there will be a current that begins to flow from the upper terminal here to the lower terminal. So what we are asked to do is we are asked to derive the expression for the charge accumulating at the upper terminal of the element for t greater than 0. Yes.
الدكتور هو ينتقل من الكبير إلى الصغير على أساس يحقق نظرية التوازن.
وش نظرية التوازن؟ وش قصدك؟
أقصد على أساس إنه يصير دلتا كامل الإجمالي يصير 0.
In this case, we're talking about applying a current, so there will be like a point where you don't have steady state.
Yeah, and is that the Kirchhoff current law?
We'll come to it. No, it's not.
Oh, okay.
I think I have to stop here, so I will continue talking about. I will solve this exercise, and then we'll continue talking about the current, and inshallah we'll conclude with the power. Okay. Any question before we?
Sorry.
Yes.
I was wondering, will be there a formula sheet for the course or not?
We'll discuss it inshallah when the time.
Okay.
Yes.
What will be the material for the next class?
What will be the material for next class? I will continue talking about this one. I'll probably discuss the power. 1.5, 1.6.
Okay, thank you.
Doctor, I'd like to ask the students if there is